manager, and he confirmed it. Okay, we should start.
We should do a scam or not scam.
It's so confusing.
Hey, good morning, everyone. This morning we have Daniel Soskin telling us about equalities and inequalities on products of Schur functions.
Hi, thank you for coming to my talk. I will tell today about inequalities and products of Schur functions. I will use notation lambda for integer partition. And let's recall that one of the definitions of Schur functions is the following. We can look at determinant of matrix their entry ij is given by homogeneous symmetric function, where I use notation hm for homogeneous symmetric. We say that Schur functions are linear bases for a ring of symmetric functions, and we call function to be Schur non-negative if it is non-negative linear combination in Schur functions. Here we have definition of Littlewood-Richardson coefficients. So Littlewood-Richardson coefficients are structure coefficients for Schur functions. Well, they appear in many different areas of mathematics. For example, their intersection number of Grassmann. And today I'm interested in studying inequalities between products of pairs of Schur functions. In particular, we could see that if we have such an equality, that product of two Schur functions minus product of other two Schur functions is Schur positive. It implies an equality on Littlewood-Richardson coefficients indexed by lambda mu from first pair and rho tau from second pair, and also some partition mu.
Is that an if and only if there?
No, it's just a one direction implication.
So sorry. So then I don't get the definition. I thought that this is the definition if this is like for every new.
Oh yeah. If this holds for every new, then yes, you can write this difference.
This is the definition, yeah?
Hmm?
The definition of
Definition?
the left-hand side is that the right-hand side holds for every new.
Schur positive.
Can you repeat the question? Sorry.
I mean, this is the definition of the left-hand side is defined by saying that the right-hand side is true for every new.
No, Schur positivity, just if you have a symmetric function, any symmetric function, you can write it in Schur basis, and if all coefficients are non-negative, then it is Schur non-negative. Here we have definition of Littlewood-Richardson coefficients, which are structure coefficients for this linear basis. We know that they're non-negative. It's from Littlewood-Richardson rule. And here I look at some pairs of two Schur functions given by four different equations. And if I have such an inequality, then I know that from the definition, I know that for any mu for this fixed lambda mu and rho tau, I have.
So the coefficient of S nu is essentially the difference of the two, right?
Yes.
That's equivalent. That's
If for every, yeah.
If for every yes. So we can ask in general. Such problem. Can we characterize four partitions such that corresponding four Schur functions form such non-negative polynomial Schur functions? So we want just to describe all such inequalities. And well, we can also generalize this problem to skew Schur functions. So let me first remind how we can define skew Schur functions. One of the definition for skew Schur function would be to look at minor of Jacobi-Trudy matrix. So we can look at Jacobi-Trudy matrix where each entry ij is homogeneous symmetric function hj minus I. And if you have a skew shape lambda mu, then a Schur function S lambda mu is determinant of submatrix of Jacobi 2D matrix given by a row set I mu and column set J lambda. They're obtained from partitions lambda and mu by adding staircase partition. And well, we can generalize this problem to characterization of products of skew-Schur functions. We want to describe such 4 different skew shapes with such a difference of products of those functions is Schur. Well, different people were studying this question, different projects. So there was a conjecture by Okounkov saying that if you have 2 skew shapes, lambda mu and nu rho, such that lambda plus nu and mu plus rho have even parts, so that we can divide them by 2, then we have such a Okounkov inequality, that the product of 2 skew-shaped Schur functions is less or equal than square such a skew-Schur function given by average of lambda and nu and average of mu and rho. So this conjecture was proved in paper by Lam Postnikov Pylyavskyy in 2005. In this paper, they proved several conjectures using same technique. So there's
That's a good question. So
Yes.
in what context did Okounkov conjecture this?
Okounkov's conjecture was coming from study of classical Lie groups. And other conjectures, this next conjecture, it was coming from studying of eigenvalues of some Hermitian or complex matrices. And so they consider different transformations of 2 partitions. Let's say they have partition lambda and mu. They do some transformations of these 2 partitions, obtain different lambdas and mu's, and then they conjecture that they have some inequalities. They have some different interpretations. We can look for these interpretations in their paper. Some of them are related to multiplicity of tensor products. Some of them are related to some domino tableau with some Yamanouchi restrictions. So in that paper, they had the following conjecture. If one of the conjectures, they take 2 partitions, they write rearrangement of all parts from 2 partitions, and they form 2 new partitions from even and odd parts, and they conjecture that these new 2 partitions give us a larger product. So if we take 2 partitions, we can take union of all parts, list them in increasing order, and then just take even and odd parts. And this conjecture was also proved by Lam Postnikov Pylyavskyy in the same paper, using the same technique as the first conjecture.
But couldn't it possibly be true that then you divide them up into any 2 ways? I mean, what's special about the odd and even parts? I mean, couldn't you just take any kind of?
No, not in any 2 ways. So we will see. It will be clear later from. There is a general rule how we can rearrange parts, then it works. And if you just take even and odd parts, it's clear that it works. If you take some other rearrangement, it will be clear that it doesn't work. But it will be clear a little bit later. So there is a there is a reason why for even and odd part.
I mean, it cannot be arbitrary way, because then it would be the other way around. Yeah, we could also treat like lambda.
Yes, that's true.
That's
That's true. It's somewhere.
Well, there are more complicated conjectures well, there was paper by Lascoux-Leclerc-Thibon. There they discussed some generalization of a whole Littlewood polynomial, and they had conjecture on some quantum symmetric polynomials that there is such inequality. And then in the same paper, Lam Postnikov Pylyavskyy, they showed that in the case that q equals to 1, it is an inequality between product of such Schur functions. And they also use same technique.
Something omitted in the last line, s lambda to the power of in is equal to.
Well, we take lambda, and then we take every eth part with step n.
And then s is omitted in the last line, right? So s of that partition, right?
Yes. Yes, it should be Schur function, not just partition.
Yeah.
So, and all of that conjectures were their implications of the inequality between product of union, Schur function given by union of two partitions and intersection of two partitions. Their union is just well, in this notation, it's just taking maximum between corresponding parts, and intersection is taking minimum between corresponding parts. And well, some of that inequalities follow just by several applications of inequality between union and intersection. And in some other inequalities, you have also, well, you can write Schur function as a minor of Jacobi-Trudy matrix, and then you have shifted in some, like shifted along the diagonal, then apply inequality again, then maybe shifted back and apply inequality again, until you prove the inequality. And you can also generalize this inequality between union and intersection to skew shapes. So if you have two skew shapes, lambda, mu, and nu rho, you can define what is union of two skew shapes and what is intersection of two skew shapes. So we take union of lambda and nu, and union of mu and rho, and also intersection of lambda, nu, and mu and rho.
So is this intersection like just intersecting the diagrams?
Yes.
So it could be empty.
Yes, then you will get back to this case. And what's the technique they used? So let's recall that we can write the Schur functions as determinants of some submatrices of Jacobi-Trudy matrix given by that rule. And basically all these inequalities we can write as inequalities between products of two minors of Jacobi-Trudy matrix. So if you have such inequality for any partitions, just using Jacobi-Trudy formula, you can rewrite it as inequalities between products of minors of Jacobi-Trudy matrix. And such inequalities were studied by Ross and Skandera, not just for Jacobi-Trudy matrices, but in general for matrices. And well, to discuss this technique, I need to introduce temporally algebra. So let's say we fix some complex number, xc, and then temporally algebra txc is a C algebra generated by the following generators, t1 and tn, such that ti square is xci, and the braid rule is destroyed. We have ti tj ti equals to ti, and well, if I and j are adjacent, and otherwise ti tj come. Temporally algebra is a quotient of symmetric group algebra by the ideal generated by one element, which is sum of all these elements. So it is obtained by sending Si to ti minus 1. And temporary algebra, elements of monoid generated, multiplicative monoid generated by generators of temporary algebra has nice description using diagrams. So we can put in correspondence to each generator ti, we can put in correspondence diagram. Let's say we have fixed value n, so we consider two columns with n vertices. And for trivial element, we just connect them horizontally. Then for element ti, we fix level from the bottom, level I, and we connect vertices on the left from I and I plus 1, and on the right from I and I plus 1. So this is T1, this is Tn minus 1. And elements in multiplicative monoid, they're obtained just by concatenation of diagrams representing these generators. So for example, if you have such expression T3, T2, T3, T3, T1, you can see this is, well, n equal 4, so you have 4 levels. This is T1, this is T3, this is T2, then you have T3 again, and then you have T3 again, which gives you a cycle, and then T1 at the end. So if you concatenate them, you'll get some picture like this, which is the picture from, for example, one of the definitions of Catalan numbers is using these pictures. You have two n vertices, and then you look at non-crossing matches. And the number of cycles gives you the power of this fixed complex number. So particularly, you could see that elements in multiplicative monoid are represented by such non-crossing matching. And now we can define what is temporally immanent. So this is a polynomial in matrix entries. It looks similar to determinant. So we have sum over all permutations in group Sn. Here we have some coefficient, and here we have just product like in determinant, xi, wi. So, well, for example, if this function is a constant 1, it's just a pair. If it's minus 1 to the power of invariant of permutation, number of invariants of permutations, you get a determinant. So here in definition of temporally immanent, we have to define this function in the following way. We take permutation w, we write reduced word for w, and then each si is sent to ti by that quotient. So we will get, instead of a reduced word product of some generators si, we get product of ti minus 1. So this is just polynomial in this generator's ti. And then, well, product of ti's can be represented by this matching, some temporary diagram. So the coefficient here, coefficient next to fixed tau in that polynomial is the value of that function. For each permutation, we will get different coefficients. Right.
Sigma is your notation for reduced words?
The sigma.
Oh no.
Sigma is this map. So sigma stands si to ti minus 1.
Can you go back to the formula?
Yes. So here,
Where's the reduced word?
well, I haven't written reduced word. We just have a permutation w. You can imagine it's a product of some si generators, right? It's a permutation. You can write permutation as product of some generators. And then each generator in this permutation is sent to ti minus 1 by map sigma.
Oh, okay.
Right?
So sigma doesn't depend on the reduced word.
No. Sigma is a map from, it's a map which was defined here from symmetric group algebra. Somewhere. Yes.
And sorry, tau, I should think like a variable ti? Tau later.
Tau, no, tau, it's an element of multiplicative monoid.
Okay, so not only a variable.
It would be a product. Well, tau is represented by some diagram like that, which is a concatenation of these TIs. And then you
Not necessarily a ti. Not necessarily.
Not necessarily. It could be one TI, but it could be more.
Okay.
Like a
And
product.
then I multiply these polynomials on the right, and I just look for the coefficient.
Right, exactly. So
Sorry, yeah, I thought if you take a coefficient of tau, don't you fix a basis, right? Which is the non-crossing diagram.
if I fix,
I mean, if you say coefficient of tau, you have fixed a basis, right? Of your
yes. So yes. So we have we just take permutation W. We write any reduced word, it doesn't matter which one. And then for each SI, you would put in correspondence TI minus 1 just by this way. So you will get, for example, S1 is to S1, you set to T1 minus 1 times T2 minus 1 times T1 minus 1. And then if you have some fixed tau, which is some Kaufman diagram, like this non-crossing matching, then you look at this polynomial, you search for the diagram, and then you take coefficient, which is in this polynomial.
I think the problem we had is that tau is not a monomial. Yeah, it's like already a reduced thing in the algebra represented by a non-crossing diagram.
Right.
I think we'll find out.
Okay.
I'm gonna do an example, or is this too much?
Yes, we can. For example, so for example, let's look what happens if you take S1, S2, for example. This is T1 minus 1 times T2 minus 1. So this is T1, T2 minus T2 minus T1 plus 1. T1 is this. T2 is such diagram. So what we have here, T1, T2 is concatenation of these two things. Which is such diagram. Then we have well, minus T2 minus T1 and plus identity. And we can ask, well, what is value of function f at tau given by such diagram at permutation S1, S2. We look at this polynomial, here it's coefficient 1. So the value is 1. If you ask what's the value of function f for tau represented by this diagram of such permutation, you look at this polynomial, and well, coefficient is minus 1. So here we will have coefficient minus 1.
I see. So if W has different reduced words, you can show that it doesn't depend on the choice.
Right.
So if tau is the identity, then what's the determinant?
Yes. So we
Can
can
you get every element? Can you get every linear combination of your?
Can I get every linear combination?
Yeah. Because you generate the entire space.
Sigma is an isomorphism, I
Probably.
guess.
So if you run over all permutations, you'll get some different linear combinations.
Yeah, do they span the entire space? So I guess.
I think so.
Well, isn't that because sigma is an isomorphism, so they have to say, you get the entire temporal algebra TS T2 or something like that?
Yes, yes. So we can also define what that means for such immanent to be Schur positive. Well, it's a polynomial in matrix entries, but if you evaluate it on Jacobi-Drudy submatrix, then it's a symmetric function. Well, and then we just use the usual definition for Schur non-negative function. So Heyman showed that temporal-Libimans are Schur non-negative.
Sorry, how do you get a symmetric function?
Well, you take temporal-Libimans and you evaluate it on Jacobi-Drudy submatrix.
Oh,
Because otherwise, well, it's just polynomial in matrix entries. Skander and Ross, they proved that if you take, they proved the Fomin identity. So we can take any two minors of matrix A, and we can express product of two minors as linear combination of temporal-Libimans of evaluated of matrix where we take a multi-set union of row sets M and P and column sets K and Q. And well, later I will describe how, given these four index sets for rows and columns, we can find these corresponding Kaufman diagrams tau which are compatible with this four index sets. So they just give the rule how we can from product of any two minors, how we can write it as a linear combination of some elements.
sorry, are there any restrictions on the matrix A?
No, it's just a general identity. This is some polynomial in matrix entries. This is also some polynomial in matrix entries. And well, they show just an identity. So this rule is a little bit more complicated. So how we define this tau? Then, because of that, I decided to look at complementary minors first. So let's take matrix A 4x4 matrix, and let's look at product of two minors given by row set 1, 2, and column set 1, 4, and row set 3, 4, and column set 2, 3. So we look, we want to construct covering on two columns with n vertices. So we take in one cover, we cover vertices from n union q, and in different cover vertices from k and p. Not here, so it's rows from first matrix and columns from second submatrix. It's a red cover, and columns from first submatrix and rows from second submatrix are blue cover. So we look at such diagrams which connect opposite covers and form non-crossing matching. For such covering, we could see that we have, well, two different ways to draw a non-crossing matching such that each edge connects opposite covers and they're inside this disk. So the rule in this theorem tells that product of such two minors is a sum over immanence indexed by diagrams obtained in this way, that they're compatible with these four index sets. This rule is for complementary minors, but in general, we just, if index sets M and P and index sets K and Q have some overlaps, we just ignore them. And we connect, well, we take these differences and then connect opposite covers. And for those overlaps, we will just connect adjacent vertices. So let's look at a little bit more complicated example for inequality where we have product of union intersection and just two Schur functions. So let's take lambda to be partition 1, 1 and mu to be partition to 0. According to Jacobi-Drudy formula, we can write it as such product of submatrix of determinants of submatrices of Jacobi-Drudy matrix. And using that theorem by Skander and Rods, we can write it in terms of immanence. What is it? So we take a multiset union of rows, which is 1, 1, 2, 2, multiset union of columns, which is 1, 2, 3, 4. This is generalized submatrix of Jacobi-Trudi matrix. And then we have covering there. We have 1 and 2 appearing in both sets. And here on other, for columns, we have 2, 3, and 1, 4. So we have such covering for 1, 4, and 2, 3. And corresponding diagrams are obtained in the following way. So for each repeated vertex, which appeared in both sets, we take 2 vertices representing one index and connect them by edge. So for 1, we have 1, 1 prime. For 2, we have 2, 2 prime. Then, well, row 3 and 4 was not involved at all in that product. So we just don't, just keep them. And then, well, for columns, each column 4, 3 to 1 appeared one time. So we have the only one option to complete the matching for that covering. And then now we can take lambda union mu and lambda intersection mu. So if you take maximum of each part of lambda and mu, we get partition to 1. If you take minimum of each part from lambda and mu, we have partition 1, 0. And according to the same rule, we write it as product of 2 determinants of Jacobi-Trudi matrix, and then we rewrite it as a sum of temporally immanence evaluated on this generalized Jacobi-Trudi submatrix. Note that it is important that multiset union of rows and columns in products of those matrices coincide. So the immanence are actually evaluated on the same generalized submatrix of Jacobi-Trudi matrix. For example, for any union and intersection, we will have that this multiset unions of rows and columns coincide. So you could see that for second product, we have 2 immanents. For first product, we have 1 immanent. So if you take difference, we will get immanent tau 2, which is Schur non-negative, and thus we have this inequality. Skander and Rods, they characterized all such products between 2 minors. They characterized differences between products of pairs of minors, which can be written as non-negative linear combination of immanence. They have complete characterization, but well, it's quite technical, so I will just tell intuitively what it means. First, we need that multiset union of rows and columns in each product is the same. And the second condition tells that, well, larger product here should be more interlaced than the smaller product here in terms of indices. So for example, here we could see that in larger product of 2 determinants, 2 covers are interlaced. We have blue, red, red. And here they're not that interlaced. We have 2 red covers going together. So going back to your question at the beginning, you asked, why do we take even and odd parts? It's because then we take even and odd parts, we have 2 covers interlaced, and we have all the diagrams, Catalan number of diagrams. But if you have, for example, some other rearrangement, it is possible that we will be missing some diagrams. For example, for this arrangement, there is no way to obtain such diagram because it will connect 4 and 1, which are of the same color. Well, so what we can do, we can take this Skander-Rods theorem and we can apply it to Jacobi-Trudi matrix, and we can obtain sufficient condition then an equality between products of 2 Schur functions hold. it's not going to be a criteria because it's a specific matrix. So some immanence could be equal to 0 on Jacobi-Trudi matrix. Thus, we will just get a sufficient condition. So,
So are you saying this Rhodes-Skandera result like immediately implies this Okounkov conjecture?
yes,
So they just were not aware of that, is why you're.
yes. You can look at the Okounkov conjecture. And if you write in terms of minors of Jacobi-Trudi matrix, you will see that here you will have more interlaced rows and columns than here. And this is also, well, it's more vivid here. Like, here it's so obvious because you have something, and here you have like literally interlaced covers.
So is the Lam Postnikov Pylyavskyy, is the proof different, or they just
No,
noticed?
that's what they did actually.
So it's like
Like this short paper.
two sentences or something? Like,
It's a short paper. It's 10 pages paper.
okay.
Can I ask,
Yes.
can you prove such things bijectively? Like the
Inductively by
bijective,
bijectively.
so the product of Schur is equal to the,
You mean inequality?
the product of two determinants equal to a sum of the immanence.
Such inequalities I prove by injection usually. So I can show that some product or some quadratic expression in Schur functions correspond to some set of those Kaufman diagrams with certain multiplicities. If I want to prove inequality, I want to build injection from smaller set to set corresponding to larger expression. So for example, just like we did in that example, we have one set, here we have one diagram, here we have another set where we have same diagram and another diagram.
I
So we
mean,
can build
the
injection.
equality, the product of two determinants equal to the immanent.
How we prove that?
I asked, can you prove it bijectively? Is there such a bijective proof?
Bijectively?
Like if you use a.
I haven't tried.
Uh-huh.
And the proof in Skandera rods, I think they just showed that they take a planar network parametrization of matrix. And they, in terms of this planar network, they computed coefficient at each element here and coefficient at each element here, and they showed that they're same.
I see, yeah.
I haven't tried to reprove that statement.
Yeah, no.
Maybe it's hard because I mean, there are negative numbers and so on. It's like really.
Well, but it's with the Schur polynomials, right? There's a positive.
That's one.
Yeah,
I
'cause
see
you-
that the immanent is.
Yeah.
non-.
Because you want to, like, for example, generalize to Schubert, where you don't have a determinant, you probably want a bijective.
I thought you were asking about the product of determinants being sum of immanents.
Yeah, but if you plug in the Jacobi-Trudi, if you use that one, you get a positive.
Okay. Well, if you want to plug in Jacobi-Trudi matrix, recently Pylyavskyy and his student Son gave a combinatorial interpretation for coefficients in expansion of any temporally immanent related on any Jacobi-Trudi matrix in Schur basis. And then you can try for immanent, you know that coefficient. And then you can look what is this coefficient in product of two minors. And well, but you will have several immanents, so you will have to take like some.
Oh.
So maybe it's possible actually. But this combinatorial interpretation is not very. So we can apply this Skandera-Roth theorem to Jacobi-Trudi matrix. So we have this sufficient condition then we have inequality. And we can strengthen theorem proved by Igor Bak, Agreta Panova, and Vyvesizov. So they fixed some integer n, and they considered maximum of all Littlewood-Richardson coefficients such that mu and nu sum up, their sizes sum up to n. What they showed is that this maximum is reached on partitions lambda 7 star, where one partition is contained in another partition. And then using this idea from this sufficient condition that indices should interlace, we strengthen this theorem by saying that maximum is reached not only on two partitions and one partition contains another one, but also they form ribbon diagram. So, well, if the coverings are interlaced, that means it's similar to staircase, but there could be some repetitions. And because there could be some overlaps in index sets, it's not just a single ribbon, but it's a ribbon diagram.
What's a ribbon diagram?
Well, it's a skew shape such that if you take anti-diagonal, there is no more than one square on this section for any anti-diagonal. Oh, for example.
And so what's the difference between a ribbon diagram and a ribbon?
Well, a ribbon diagram can be like a couple of ribbons, for example.
So a ribbon is connected.
Yes, here ribbon diagram would be something like that, for example. This, and this part is appearing because we could have some overlaps in index sets.
So is the point supposed to be that like lambda star is equal to mu star, or should be equal to mu star, but like because you know that can't always happen?
They're close to each other, but they're not equal, I guess. So then you look at this, well, you still have different, you should have some elements in set difference, right? Which are of two different colors. So the number of these elements is fixed. So you cannot just, if they would be equal, you will have no squares in that ribbon diagram. So that would mean that everything is overlapped. But actually, we have a fixed number in the symmetric difference of two sets. What I mean by that is that in this example, you do have a fixed number. You have two blue vertices, two red vertices. You can shuffle them the way you want, and you will get different products with different values. But you will still have two blue vertices and two red vertices, which will end up in a fixed number of squares in this ribbon diagram.
Okay. Is there like a reason, like a heuristic why lambda and mu should be close to each other?
Well, I guess just because maybe it's not a good answer, but I think it's just because of this sufficient condition. So what is happening here? Here we are looking at lambda and mu plus staircase, and we want lambda plus staircase and mu plus staircase interlace. And this is happening when lambda and mu are sufficiently close to each other.
Okay, gotcha. And sorry to keep asking, but do you know what mu looks like at all?
No. This proof is by contradiction. If you assume that there is a square, if it's not a ribbon diagram, then you have at least one section of length 2, and then you can show that you can shuffle them more and increase the product. So it doesn't really tell us even if maximum can be reached not by on some lambda mu which do not form ribbon diagram. It just tells that if you want to find maximum, you can search among ribbon diagrams and find. And there was also another conjecture in the paper by Fomin Fulton Li Poon, which was not proved by Lam Postnikov Pylyavskyy. And well, it's just we obtain an equality. We fix two partitions lambda and mu, and we construct partitions lambda star and mu star in the following way. So in general, several people tried to prove this conjecture, but it didn't work out. And we decided that if we add extra condition, if you add staircase to partition lambda, staircase to partition mu, and also for lambda star and mu star, and we require that multiset union is the same, so that we are in the necessary condition which we just discussed earlier. Our necessary condition works only in the case their multiset union of rows and columns coincide. Over here. So we know how to compare products of minors of Jacobi-Trudi matrix in this theorem. Then multiset union of rows and multiset union of columns is the same. So if you look at such conjecture and we require this extra condition that the multiset unions are the same, then we can see that this conjecture actually reduces to the case which we can show by necessary condition from Skanderov's idea.
Sorry, is it possible to say easily what the star does? I mean, I know there are definitions here, but
well, if you look at lambda and mu plus staircase, then if you look at E of lambda star and E of mu star, it's obtained from E of lambda and E of mu in some sense by trying to sort them. So we have two index sets, E of lambda and E of mu, and we fix some element. We count how many elements are smaller in lambda rather than this fixed element, and how many elements are smaller than this fixed element in other set. And then we take this delta and shift by this delta the given element. And the difference here is that we do it with non-strict inequality and strict inequality. So in some sense, we sort of, it is possible that this multiset union is not preserved. But if it is preserved, then we basically just shuffle elements in a way that they interlace.
Isn't this I of lambda just sort of what you do by turning a partition into like a Grassmannian permutation? Isn't that like the first part of the Grassmannian permutation?
Yes.
Okay.
So somehow this is like, I'm just saying this, it's somehow it's related to the permutation corresponding to lambda.
Yeah. Well, I think this conjecture was motivated by some dimensional argument in their paper from representation theory, but they formulated it purely in discriminatorial terms.
I think it would be helpful to do it again, if you can.
Of that inequality?
No, of the star.
Of the star?
But if it's not, just don't worry about it.
Maybe after end of the talk. 10 minutes. So some researchers, they also looked, then we have equalities between product of Schur functions and skew-Schur functions. And Jan proved unique factorization theorem for Schur functions. And then also Rainer, Shaw, and V.B. Genburg studied coincidences among skew-Schur functions. And as far as I understand, even to tell when two skew-Schur functions are equal, I think complete classification is still not found.
What does the unique factorization theorem mean?
If you have a product of several Schur functions, and you can say that this product equals to other product of several Schur functions, then it means it's just to take same Schur functions and maybe up to permutation. So it's like unique factorization in prime numbers. And well, we decided that it's natural to look at equality conditions in the sufficient condition coming from Skandery-Rhodes theorem. So we have the sufficient condition from Skandery-Rhodes theorem on these 8 partitions here, then we have an equality, and we can ask when the equality happens. For example, it will tell us when the equality happens for product of union intersection as lambda union mu times s lambda intersection mu equals to s lambda mu. From Skandery-Rhodes theorem, we could see that, well, if we have conditions satisfied in this necessary condition, then this difference is just a sum, certain sum of temporally immanence related on Jacobi-Trudi submatrix given by such multiset unions. And if you want to have here equality, we need to answer the question, then each immanent is such summation equals to 0. So here those indices, those diagrams kappa in that summation, they should be from the first covering coming from first product, but they should not be in the second covering, in the second covering coming from the second product. So if you go back to our example, we could see here that immanent given by Kaufman diagram tau 2, it is in the second covering because this particular diagram connects vertices of opposite color for covering coming from second product. But this particular diagram do not fit to the first covering coming from first product. So in this case, this difference phi bar would be just tau 2. And to answer the question when we have equality condition, understand then we have equality to 0, we need to understand then all the simulants are equal to 0. So it's a natural question to ask when a temporally immanent given by some fixed Kaufman diagram tau for some fixed Jacobi-Trudi matrix equals to 0. And here I will switch from multiset union of columns and rows, which give me a generalized Jacobi-Trudi minor. I will switch to notation with 2 partitions rho and mu. Their submatrix of Jacobi-Trudi matrix given by 2 partitions rho and mu is given in the following way. Each entry ij is a homogeneous symmetric function h rho I minus nu j. We can just define any submatrix also using pair of partitions. So to answer this question, let's recall what is a path matrix. If you have a planar network, these oriented edges, like here, let's say all edges are oriented from left to right and from top to bottom. And we have some weights on faces here. Here we have 9 weights. If you want to find entry of path matrix indexed by indices ij, you take all possible paths from I to j. You take sum over all possible paths from I to j, and we sum weights of each path, which is the product of weights under the path here. There are other ways to define path matrix as well. And for path matrix, we have Lindstrom, Gesselin, lemma, which tells us what are minors of such matrix. So for example, if we have a path matrix given by planar network parameterization, and we have index set for rows I and index set for columns j, minor ij is given as sum over all non-crossing path families, which starts at vertices indexed by rows and ends at vertices indexed by columns. So, for example, if you have minor 1, 2, 1, 3, we look at all non-crossing path families going from indices 1, 2 to indices 1, 3 here. So in this case, it's just two possible path families which are not crossing. So we will have just sum of two monomials. And there is analogous theorem for temporally immanent. So let's say if you have a path matrix, we can tell what is the immanent for a particular, for fixed diagram tau evaluated on this path matrix. It's very similar to Lindstrom lemma, except now we take sum not over non-crossing path families, but we take sum over possibly crossing families, such that maximum two paths can cross at one point, and if they cross, they resolve like here. So if you have two paths crossing, they should resolve, well, green starting from 3 will continue this blue starting from 2, just like on that picture. And we will end up with Kaufman diagram of that shape. So in this Lindstrom lemma for immanence, we take sum over all path families which resolve in this fixed shape. Here, if we fix shape tau2, it's T2, and we want to look what is the immanent related on path matrix given by such network. We have only 4 possible path families which resolve in this. If you take a trivial element given by horizontal edges, then you will just get a Lindstrom lemma like it is classical version, because it will be non-crossing path families. For example, here you can see you have two non-crossing paths, and they would correspond to trivial diagram with 2 horizontal edges. So we have lemma which tells us when immanent is strictly Schur positive, and it's quite technical. So if you take any Kaufman diagram, it can be written uniquely as such products of consecutive intervals of generators Ti. And then using this version of Lindstrom lemma for temporary immanence, we can study then we have at least one path family which resolves in a necessary diagram. If you have at least one path family, then immanent is strictly positive. If you don't have such path family, then it is equal to 0. And we can understand when we don't have any path family resolved in a fixed Kaufman type tau, then we have such system of inequalities on rho and nu here, which gives me a fixed Jacobi-Trudison matrix. Okay, and well, if I want to have equality in this inequality, I need that all immanents in the difference are equal to 0. So I need that for each immanent in that difference, at least one inequality in this system is broken. Well, overall, I have like exponentially many immanents in the difference. But in fact, we can show that we can choose n subset of size n squared, for which we can show if system doesn't hold, then for each element from this subset. Then for all other immanents in the difference, system doesn't hold as well. So it is enough to check, well, it's constant times n cube many inequalities of that type to tell if you have equality in this inequality or we don't.
sorry, I just want to make sure. So in this previous lemma, this immanent being Schur positive, this simply means it's non-zero.
Yes, greater than 0.
Oh.
Well, this is Jacobi-Trudi matrix.
Yes, but it's always like Schur non-negative.
It's Schur non-negative, but it can be also 0.
Just completely zero.
Yes.
Okay, so it just says not completely zero.
Exactly. So we are trying to figure out, then we have equality and inequality. This, suppose we have this condition, then we have greater or equal than 0.
Yeah.
And we are trying to understand when it is equal to 0.
But instead of writing Schur positive, I could have just written not equal to 0.
Right, you could write this.
Also about that, so in this lemma, could I replace the Jacobi-Trudi matrix? Like what kind of matrix could I put there? Is it a triangular tuplets matrix of indeterminates or any triangular matrix of indeterminates? If I just want to know it's not 0.
I think you can, yes, because it's this idea is this system is literally built from that theorem. So you will have to understand also how you parameterize your matrix. Jacobi-Trudi matrix is parameterized in a standard way. We take lattice network, and if you want to parameterize Jacobi-Trudi matrix row nu, we take vertices at row I plus infinity and vertices and nu j1, right? This is a standard parameterization.
Oh, I see.
So then we go back to the lemma and we ask, where should the vertices be located that I can have path families crossing in a way that their resolution is our fixed sigma?
Okay.
So it also depends on how you locate your vertices. Maybe if your matrix is given by path family with different arrangement of vertices, maybe they always intersect. So there will be some restrictions on position of vertices. Yes, but I think similar idea could work for each particular explicit network. You just study, then you have certain intersections. So here that it is equal to 0, that means that location, that this Jacobi-Trudi submatrix is given by two partitions such that those vertices are located in a way that there is no family resolving a given type tau. And well, here we find that we can actually just study a small subset of immanence in that difference. And if you check that all of them are equal to 0, the rest are also 0. So we can actually check in polynomial time if all those inequalities are equalities actually. And also on the theorem which I mentioned earlier, we have a combinatorial interpretation for evaluation of given immanent on given Jacobi-Trudi matrix expanded in Schur basis. So if we fix tau, we fix some Jacobi-Trudi matrix H rho nu, we can expand evaluation of this immanent on that matrix in Schur basis, and there will be some coefficients. So there is quite technical combinatorial interpretation of these coefficients. I don't want to define too many definitions to describe this combinatorial interpretation, but we do have this combinatorial interpretation. So using this combinatorial interpretation and that formula for the difference given by summation of immanence, we can show that difference between two Littlewood-Richardson coefficients is in sharp P class. And we can also actually, well, not for Littlewood-Richardson coefficients, but we can actually write for any coefficient appearing in this necessary condition coming from Rod-Scandera theorem. And so this is the last slide, but I can also tell what we can do for future directions. Leonardo suggested that we can look at sλsm classes, and it looks like similar inequalities work for sλsm classes. and also for, I think for Poincare dual successor classes. I can see that inequalities, this type of concavity inequalities, they can be reduced to inequalities between quadratics in Schur functions. So we can use similar ideas to prove that as well. Thank you. Yes.
So here you're considering like Schur non-negativity, but there's other weaker notions of non-negativity, like monomial non-negativity or pointwise non-negativity on the negative orthid. Are there any interesting?
Well, there is
Problems with
positivity, not on negativity. So I started inequalities between products of minors for totally negative matrices. For example, here we have difference between products of two minors expressed as some combination of equals. So we can show that this difference is non-negative if and only if this combination is non-negative as well. So if you have two products of minors, we take their difference. If in the difference at least one immanent is coming with negative coefficient, then we can find totally positive matrix making this difference negative. So they're like delta functions in some sense. But for then they're related on the Jacobi-Trudi matrices, it doesn't work this way because it's not, this matrix is very specific. And if some immanent is negative, it doesn't mean that the difference, we don't have an equality anymore. We can still have equality.
So you can have more inequalities for Schur functions.
Yes. You can also try, well, I tried to check if immanents are non-negative on Hermitian matrices. And on some of Hermitian matrices, for example, bases, immanents corresponding to basis elements Ti are non-negative on Hermitian matrices. But some nested pictures also correspond to non-negative values. But there are some immanents which are not non-negative on Hermitian matrices.
So an immanent can be negative on positive matrices.
Yes. For example, T1, T3 for 4x4 matrix. But you can find some immanents which are product, for example, like two symmetric minors, like that. And then it's going to be product of two conjugate things. So it should be positive. For example, it will correspond to, like for 4x4 matrix, it will be this type of picture. But for example, if you have product of two generators which are far away from each other, then it's negative for some reason.
I don't remember exactly what this was about, but wasn't there like a conjecture that like among immanents, permanent is the largest and determinant is the smallest?
Yes, this is for totally positive matrices. It's a permanental conjecture.
Oh, I see.
And in the middle there is a sequence, I think, of characters.
But not for positive definite matrices. Right? For positive definite matrices, it's different.
Yes. Yeah.
Are there similar results for example, monomial symmetric polynomials known by you or anyone?
Are there results for monomial symmetric polynomials?
Yeah. Products of them and having inequalities.
There is there is this inequality which was in Barcer-Brandon paper for averages. And they proved it actually. Well, there are some inequalities on expression which is quadratic in minors of Hermitian positive semi-definite matrix. And they showed this inequality somehow using some analytical techniques. So I tried to prove this for totally positive matrices, and we can also use monomial trace immanents. Here we use all immanents we use here were temporally immanents. But there are also monomial trace immanents. So
I don't know what that is. I was thinking if you multiply monomial symmetric polynomials together, are there any inequality among them?
Well, I haven't tried to prove any inequalities of that type.
Okay.
Maybe there are some.
What's monomial trace immanent? What's that?
Well, we have a monomial basis for symmetric functions.
Yes.
And so we can define, well, in temporally immanent, we have this function f tau, which was defined using reduced expression for permutation. And there is also a way how we define the immanent for monomial basis, somehow combinatorially, but I don't remember it right now. It's in Stambridge paper, conjecture on immanence. So it will be, well, different set of coefficients in immanent. For well, okay, I don't remember that statement precisely. I'm not gonna say it. I think that okay. So I think if you look at immanence, which are defined by functions which are constants on conjugate classes of permutations. So if such immanents are non-negative, meaning that they're evaluating to non-negative values on totally non-negative matrices, then they form a con. And I think monomial trace immanents are generators of that con. That was a conjecture established.
Okay.
Okay, let's ask more questions after thanking Daniel for nice talk.
I think that's it's so clear. I was wondering if there are any questions about anything about
Look at matrix sugar varieties.
Argument that
I think about this intersections.
And there is
we're doing it very naive.
Yes, that's right, yes,
I'd like to go into the university.
I was also thinking this last theorem that is in previous slide, this could be a path towards a previous solution.
And try to generalize it. If you take broader.
On previous path, they said what's the coefficient of S lambda.
If you have predetermined.
Once you have it, once you sum up, there is at least a chance.
Then you may.
something like
Bijective. Sorry, I much later understood your question.
Interpretation from transactions.
matrix.
There is like some approach. Or
Sorry, you have one to place. We have one.
it's not as good.
Okay.
I thought the talk was gonna be 2 hours
Yeah.
because it's only one talk, but apparently not.
If you know the answer, you will be able to say something about complete pictures of it.
But do you want to be sure positive?
It's where there is.
The lambda star,
I want anything on
you should, okay, for the last time, the size of set I, etc., like that set, is it like usually very small or
An identity.
we don't know.
Which set?
Like
But what inequality of like.
this one,
No, it's not necessarily small.
Okay.
For example,
I don't have.
A.
well, let's say you already.
What does it mean for something general?
E lambda. E lambda.
You have polynomial, right?
But yet it's still
Permwise,
respected that formula.
Okay.
So it is
no,
possible
it
that
doesn't have to be that. You can plug in non-negative numbers
for example, smaller than
and then you can say.
yeah,
so then you will have a large.
A minus
Yeah.
B is always non-negative.
Fair. I think like.
Wait, you're referring to
Right? Like
No.
this
Your-
object, and you mentioned.
Jesus calendar.
Oh, yeah.
A minus
So it's
K
like
part,
lambda is
it
greater
feels
than
like
mu
it's
and
very
delta
close,
order.
and you like decompose.
MUIR.
But I think maybe I'm just like looking at things that's not related.
There's like super.
We apply
What I was doing it.
matrix.
Well, I don't know right away if it
But
is.
yeah, it's as if lambda is greater
Of course,
than mu and delta.
that's how numbers show up in many different.
Yeah, it's like.
Yeah,
We
lambda.
should say
Maybe you can see some. I don't know.
is bounded above by a product of smaller sugar.
Maybe you need.
Yeah, and like the ribbon diagram, it feels like a ribbon diagram.
So I don't see.
Yeah, like
So like the simplest case,
last
it's
time
like
when something like this.
I don't know enough
choose
about
the relation to
right?
two
It was
zero.
like the result was like tracing
That's
the
just like
path
X
of the
plus
ribbon
Y squared.
diagram, and somehow
That's
that
right,
is
equal to
my
the
traction
X
was
plus.
like.
Yeah.
Maybe
this
this.
path,
What's the
So I don't, again, I think I'm responding to things that.
Yeah, I want to exit, but maybe, yeah, I don't
Is
think.
A
yeah, actually.
In terms of if you have products that are.
For every
anything.
non-negative vector.
Of course, you can just take products
of that accent.
Oh, and for the lemma on page 22,
Yeah, so
we
this is
have this
not.
like nice condition for how that we need to satisfy.
Yes,
Um,
yeah.
I can't quite.
I mean,
type
coefficient wise, there's not gonna be.
mentally, but is it like a visual
yeah,
way
I
to
thought-
understand
I thought
that
it's
how?
that.
Actually, we both like, we have to think about them as variables. and-
Coefficient wise.
So in
I
the
don't-
middle,
yeah,
you have the
point-wise
tau.
better.
And then the
And
A to.
Well, it's weaker.
Power.
Well, whenever you have
Yes,
that
but
picture,
it's-
like any type of picture like that.
Yeah.
Stronger in my context.
You can write it
Ah,
as a product
You're gonna
of
get more.
generators, TIs.
Yeah, that boring.
So that they're every time, well, they're consecutively decreasing. You have, let's say, T3, T2, T1.
They get
I hear him say what you
T1 or so and so on.
Okay.
You have this also restriction.
Thank you.
So you have one interval, then you might have another interval, another.
Okay, I got the A or the B.
So you're describing where that
This will
like
be just.
crashing, that the twisting shape
Yes,
should
yes,
be.
yes.
Oh, that's pretty, oh, thank you.
Matrix Schur variety.
Okay, thank you very much.
Yesterday's version lives in.
Are you waiting for the next talk?
I think
yeah, let's
this
start.
we are quite different.
That's a 1 hour talk.
A is a linear
And
combination.
Ah, okay.
You could have given it 2 hour talk.
But I didn't prepare it well.
So
What
You
happened
could
to
talk twice as slow.
like the matrix
Huh?
were variety?
You could just talk very slow.
I already talked very slow, did it?
That was normal.
Okay.
Oh,
I thought I had very short talk,
Smaller
and then I had to talk very slow.
varieties of
Ah.
that kind.
Anyway, interesting.
At least when I.
So by the way, this multi-set union condition, this is saying somehow it's like homogeneous. So like if you converted it to,
Yes,
The grass
yes,
line,
yes,
it's saying-
yes.
it's saying if you act
Yes.
by this positive torus,
Yes,
this will not change.
I don't know, but if you
For example, there's this like conjecture of Fomin
work it out,
Fulton Li Poon.
so just apply our inequality
It's not
to
homogeneous.
matrix Schur variety in
Yes.
multi-projective.
Yes, that's why they didn't do it.
Ah,
I think you get
Because
something.
what they were using, they were
Inequality.
trying to use immanence.
Sure.
Their paper is on using immanence.
I also remember there is
And immanence,
also.
well, if you don't go too deep, you just
You
want
have to do
to have
something.
everything in level of immanence.
yeah.
As long as they have a negative combination and immanence, we're happy.
The reason why we cannot.
So they did all the conjectures they can do just using immanence.
We can.
And here, in this Fomin Li Poon,
Ah, so this is the case where you have a negative.
you have negative immanence because you don't have, yes, here you have like the product, you have its own Jacobi-Trudy
We don't have anything about
is its
coefficient
own multi-set union.
No,
If you already point, which is
Point-wise.
So you have immanence living on different submatrices.
Yeah.
Jacobi-Trudy matrix. But because they have like, if you just, let's say, shift it along diagonal, it's not a problem.
Generally
I
inequality.
think it's just the same thing.
Yeah, gotcha.
But
For
in
certain.
general, it's more complicated.
Okay. So maybe you.
So you apply those.
Yeah, I think if you.
By the way, I mean, so being sure not negative, that's saying it's a, like there's some, you know, at SN module, the SN module associated to it. Are any of the proofs, like, are they like using the fact that you take a character of
I got
S
the
mod,
real question.
or is it,
For inequalities?
yeah,
Well, I haven't seen it.
for example, like
I-
road scan there, I actually don't.
So, I mean, you can like ask.
How they proved
that
that
it by to a certain
Just
point,
how-
S by
there's no negative.
or
Oh.
H or something, is it?
Well, yeah, so in Skanderov's paper, they have this
You
sequence.
just told
And
me
they
that
proved this
theorem called
this Lindstrom
theorem.
analogue.
What there?
Mirror.
Okay, so they just prove everything combinatorial.
Oh,
Yeah, no Haman.
Yeah, his.
That paper I don't understand. They proved this.
I'm just
Okay,
uninformed.
This the matrix guy.
Matrix guy,
okay, so it could be.
But you know this
representation
paper,
theory. No,
such a thing, or
I mean, I know of it.
lambda is bigger than mu and dominant.
I don't know.
Then.
It's-
I mean, I'm just wondering because like I mean, for me, that's like one of the main motivations for considering Schur positivity is that it means, if you have something which is Schur positive, you have an SN representation.
Yes.
About products.
But here it seems everything is just done.
Here I was
Combinatorially,
understanding
so
that.
that's kind of interesting. I mean, as combinatorialists, I like combinatorial arguments. On the other hand, you can ask what is the SN representation? Like, can you construct?
The more balanced
Can you
exponents
construct?
you have, you can say that
An
arithmetically
injection
geometric is like
or,
1-0.
product of Schur functions is a product of GLN representations. Can you find an injection?
There is something
And
Rajan
generalizes this
something the way.
dominance
For
order.
example, that unique factorization theorem, he proved like using representation theorem.
This is the one I said.
In terms of representations.
More balanced, it's smaller.
I think Leonardo was asking a question. So it looks like for srsm classes for Poincaré
Consider your partition as exponents, you prove everything and sum up. More balanced is smaller, and more balanced means smaller,
for small examples.
Yes.
the dominance order.
Okay.
I was a little
Srsm
bit
classes, if
confused.
you take the Soskin
I'm
cavity
trying to
equality,
compare these
you can expand it
inequalities
in
with our.
Schubert expansion.
I always thought that in our
And then
inequalities,
it
more
reduces
balanced,
inequalities to quadratic
smaller.
in Schur's, which you can still.
But
use
then
in type of
they also
difference.
deduce Okounkov's conjecture from this more general inequality. Which that one seemed like log concavity in Schur polynomials. That one looked like the usual.
Yeah, it's interesting, because like this,
I'm.
like this stuff, June does prove it positive.
Because-
It seems it's all coming from
The Okonkov
projection.
bigger one.
Yeah, I need to read this Hammond's paper maybe.
So,
Because for me, it's just like, okay, let's just prove that conjunction. I remember. So I see some conjecture.
Divide by two.
no.
I mean, I know what it looks like.
I don't know.
I see somehow. Like an intersection were bigger than the two things. Those inequalities,
Oh, yeah.
while for us usually sum and intersection are smaller.
You were asking some question.
I mean, isn't this more balanced?
Fixed basis at the beginning.
Oh, yeah,
So
yeah,
it's like,
Oh, no, I was just.
This is like log concavity, right?
I was just.
Yeah,
being
but then
fast.
the-
No, I'm saying, when you say if you take a
Other-
coefficient of tau,
More general
Right.
thing, right?
like,
Union times intersection and so on.
you need to already have chosen a basis of the.
That one looks like
Of the
other side, just more unbalanced.
yes, yes.
Yeah.
It shows the.
You see my confusion?
Yeah, I see my confusion. No, I'm also confused.
Well, this LLP thing is also balanced is bigger.
And you were thinking it's not fixed.
This is
That's true.
Well, no, I was just,
balanced.
Oh, yeah, sorry, yeah, this is.
So why is this?
because also I think other people were.
First of all, this is different, because there is.
Yes, I noticed. I noticed.
Oh, so there's no skipping. Is that important?
Yeah, maybe.
I think mu to be empty.
Oh,
and
wait,
rho to
there's
be
no
empty.
skew here? There's no skew here? Only skew
Oh, right, yeah.
in here?
Okay.
Oh, maybe that's important.
Okay, what if you take mu and rho to be empty?
No, I had it differently with them. I had it with Q.
Oh. Oh, this is, sorry, this is Q.
Oh, there is single S, not
Yeah.
not two
Yeah,
S.
okay,
This
I
is single S.
remember. Yeah,
Oh,
yeah.
I see. Okay,
Yeah, yeah.
then I take it.
Sorry.
I take it. I see.
I need to correct.
Right, but it's the square of that. It's the
Yes,
square of
it's
that.
the square of that.
Exactly what it is.
It does look like
That's right.
log concavity, but.
No, that's just because I was talking
Because the guy
about
was-
public.
I mean, it's hard to say how this is. related.
but I was surprised.
Yeah, Goreski also, he occasionally goes.
Sometimes
Yes,
it still gives you the impression that this part is more balanced.
Okay,
But
Yeah, I
here.
guess he gave some
it
lectures
gives the
last
impression that this part is more balanced.
Yes.
And the union and the.
Maybe I
Theory.
missed.
From that.
Maybe it wasn't part of
I
this.
agree.
Okay.
Yeah,
He told me he's not employed yet.
yeah. But he's McPherson's party.
So
So I don't think he ever
functions
had.
and partitions like more unbalanced,
I don't know what kind of position he had,
I see.
that's the bigger side.
but of course, a very accomplished mathematician.
Oh, okay.
I mean, it could be consistent with the matrix Schur part, I suggested. Right, so on our smaller side, we'll have some power of Schur polynomial. And I imagine on the bigger side, I will have product of Schur polynomials, each one corresponding to maybe deleting a row of boxes. My diagram or something like this. Right, so it looks like this side is more unbalanced. That this part is pure power, so it's completely balanced. So it's okay, it's consistent.
I was gonna say that. This is a more unbalanced partition.
So we're just asking.
No, but you need
if
two
you
partitions.
Take any one of the.
Somehow, when
inequalities of
pairs
S
are balanced or
of something
Okay.
that occurred in your top.
somehow
Just
three
replace
and the
S
box
by E
seems
or H.
less balanced
or
than two
M.
and two.
Okay, if it's true.
Is it
But
like
if you
literally
fill
true
it
without
in-
further modification?
I don't know.
Modification.
I was gonna, okay, oh,
I
this is a heuristic, I guess. This is like x1 plus this. This looks,
Demons are not H positive.
This is this,
Not
this
H
is-
positive. Technically, demons are not H positive.
sorry.
This
I got
for me
confused.
would be x1 times x2.
But
Yes,
that
this
does
is,
not necessarily contradict the inequalities,
and
right?
then
Because
2, 0.
Yeah.
we
that's not
we also
contradictory.
don't know that
No.
whether the difference is a
X1 squared plus
non-negative
X1 x2
combination
plus
of
X1
units. So if I replace S by something else.
Yeah,
Yes,
Yeah,
yes,
so
yes.
it doesn't
Yes.
logically rule out the
and
possibility.
then you have,
The
Yeah,
difference.
it is-
The intersection for me would be just one box.
Difference may be a non-negative linear combination of some things that are not immanents, and those
And the
things
union
may
would
be
be
a
like-
negative
Yeah, maybe it's
combination.
completely unrelated.
okay, this is, it's just two terms, right?
Yeah, I think it's x1 squared x2 plus x1 x2 squared. If we are just using two variables.
Yeah, so who is more? This product versus.
So this product is bigger than this product.
Yeah. Okay. So who is more balanced?
Well, I would say these two are more balanced than this two.
I said, but if the inequalities, if I get by replacing S by E or H
Mhm.
are maybe not so interesting. And if it's true, we can prove it. It isn't like E of a lambda by definition a product of these.
Yes.
So maybe our question reduces to a question about like just elementary symmetric polynomials. And it's about like some product larger than some product, so. And just
Deduce the statement for ease from those statements.
Is it union intersection inequality or what's the inequality? On this.
yeah, charge they just the union intersection. Should we start from that?
Okay,
So some things are gonna get cancelled, by the way.
I can, so if we have. Well, we can think about this, but I can tell you why I asked the question I asked.
The comment I wanted to make was that maybe if I replace S with E on the union intersection inequality,
Yeah,
maybe it just reduces to the case when lambda and mu have just a single row. Maybe we have the inequality like row by row in the Young factor.
Mhm.
And therefore it's much easier to prove if it is true. So it feels like the inequality just reduces to just
a product of.
But for one row, it's equality. Not inequality, it's equality. Well, if you take intersection, it's just the smaller, if you take the union, it's just the larger.
for one row, it's the equality. Can we do one example where I have two rows?
Yeah, so we just did one.
Oh, you did one? Okay.